Hi, Miss Titus. How are you? Um, yeah, I just wanted to give you some details about all the math I've been using for my work, all the stuff you've taught us. So anyway, um, so I make games, and right now I'm using this software called Unity 3D to make it. And yeah, so this is it. So first, let me start off by saying that you need math everywhere here because you're dealing with like either a 2D space or a 3D space. In this case, it's a 3D space. So if you see this is my game editor. So it tells me how the game looks completely, like the whole world of the game. And the window on your left just shows you how you see the game on your screen. So um, this is my map, and it's placed on the XZ plane and y is straight ahead. So if I rotate it, you'll see the axes here. So you see y is right on top, and x is from left to right, and z is from up to down. So if you so you rotate it, and everything rotates in 3D space. So everything you place on the map has like a you know 3 point formula. I mean a 3 point position. So you have an x, y, and z as well as a rotation. So if you're looking at say this pink thing which is supposed to be a power that you collect, so you go to a the power, uh, this one. Right now it's already rotated by 90 degrees, so if I make it 0, it's gonna lie on its side. Let me zoom in so it's easier to see. God, yeah, so it's on the side now, right, as compared to the other ones. Like this one, this one is straight. Yeah, so that's exactly. So basically everything just relies on vectors and coordinate geometry. So anything that you do, if you want to apply a force, if you want to change the behavior of how an object moves, everything is controlled by its position and its rotation, and even the force that you apply is applied by a three coordinate vector, because again a force has direction, right? So that's another reason. Yeah, I'm gonna change this back. Yes. Okay. So uh, earlier when I was posting that code online about what I used for my game, the basic coordinate geometry, what I needed to do was, now if you see right now the camera is stationary. So if I play the game, I control the blue guy, the blue ball, and my opponent is supposed to control the red ball, but it's supposed to be over the network. So right now there's no one else controlling the red ball. So what I do is I apply force on the blue ball by clicking and then pulling, pulling to add force, and then moving him to change the direction. So you have an arrow there. So yeah, so apply it, and then he moves that way. Now this camera is stationary, so if I go off camera, you can't see him on your screen on, say, if this is your phone. But if you see on the editor, this shows you the whole world, right? So he's still over here, but your screen is only around here. So what I wanted to do was basically have the camera follow my ball, and the opponent's camera follows his ball on his device. So on my phone, this camera is only going to follow my ball. So this guy can always go off screen, but my ball can't. So let me do that. So now it's going to follow my blue ball everywhere. So if you see on the right side, the camera is also moving. So the screen is moving basically according to my ball. And so what I wanted to do was, it's going to be a problem if the enemy ball goes off screen. You don't know which side he is going towards, like no basic direction. So I wanted to add a arrow for when he goes off screen to point in the direction he is in, so that I roughly know like how to deal with him. Like if I collect a power and I want to use it on him, I don't have to search for him all over the map if he's gone off the camera. So if you see, this arrow is pointing in his direction. So if I go straight towards that, I get to him eventually. So and the arrow has to be dynamic, right? So it can't like, so if he's gonna move somewhere else, he's not gonna be stationary, correct? So it's gonna change according to our relative position. So how did I do this? It's basically I just used, just the straight line formula and the slope form. Pretty much just the slope formula. So if you see, I've drawn a vector. If you see on the right side, let me just, yeah, Paulo, 1 minute. Yeah, that's too much. Okay. So if you see on the right side, I've drawn a vector from my ball to his ball. So the vector is in this direction. It's say this b and that's a. Vector a b is equal to b. Vector b minus vector a. That's it, right? So I've drawn a line and calculated the slope, which is nothing but z2 minus z1 divided by x2 minus x1. So it gives you the angle of this, the tangent of this line. But you want the arrow to stay within the bounds of this camera, so, and specifically basically this box, or not even including this bar, so this box. So you figure out the slope between these two, and you know that if it's along this line, the arrow, if it has to be along this line, then you know that the z position, which is technically in normal math terms your y direction, your y position, but over here it's z because y is straight up coming towards you through the screen. So right now you know that the z position is constant, and you know that the slope between this ball and this arrow is the same as the slope between your ball and that ball. So just equate the two slopes, because you know the slope already for this, and you know the x position, sorry, the z position for this. So calculate the x. Simple, it's a simple equation. So that's how you get the position for when the slope is less than the slope of the diagonal. I mean, sorry, greater than the absolute slope between these 2 points is greater than the slope between the diagonal, or the absolute slope between this diagonal. So it has to be such that the z position is constant at this value. Same thing up above, but if you're going to the sides, then the x position is, let me like go to the side, yeah. If you go to the sides, the x position is constant. So instead you calculate the z of this value. That's it. Okay, so that's one thing. But if you look at this arrow, like, let me pause this. If I'm looking at this arrow, let me click on that arrow. Now the arrow is just another game object, just like this ball. So it's a physical thing I place. So it's got its own position and rotation. So you're setting the position fine, but how are you changing the angle, right? You have to change the angle of, see, without, if I'm going to just let it be on its own and enable this, yeah. So the arrow is constantly just pointing towards the left, because you're not doing anything to it, right? So you have to change the rotation. So if I change the rotation in the Z to 90 degrees, it's going to point downwards. So I have to change that rotation according to where the line is. So even there, if you see, I've basically just used I've basically found the slope and used the arctangent formula to calculate which angle it should rotate to. So first I calculate the arctangent of minus of the slope, and I just convert it's in radian form, right? So I have to convert it to degrees. So use another equation here. So you say rotation for whatever in radians into 180 divided by pi, which is nothing but math of but dot pi. Yeah, by pi will give you the same value in degrees, and then you apply it to the arrow, and then you rotate it according to whatever it needs to be. So that's it. So that's just basically one example. So I use it everywhere, and in this case I have another functionality here. So I collect this power. So say it's a laser beam or something. So I collect the laser beam power and I use it. So I click on the power, aim using the same way I move, but he's stationary. Only thing, the pointer moves, and you release to shoot a beam, right? So in this case, I had to do a number of things, and this is, at least the earlier one was basically scalar geometry, but this is vector geometry because I have to literally cast the ray in the direction I'm aiming, and for that I have to basically take the vector from A to B, normalize it so I get just the direction as a unit vector basically. um, Let me see where I've done that. Power manager, okay. Yeah, so I mean, it's hard to understand when it's in this sort of syntax, this code, but it's essentially just taking the position, the vector of your current, of where you place your mouse or your finger on the screen. So that position, and it uses a parallelogram formula to calculate a parallel vector in the same direction. So in case I'm clicking here and pulling this side, it's like a parallelogram, right? Because I'm shooting this way, I don't have to click on the ball to ensure that I'm pulling exactly in that direction. I can pull anywhere on the screen. So this AB, it's a diagonal of a rhombus or a parallelogram, and I'm just using that formula to calculate the vector here, and I'm using that vector, normalizing that value just so that I get a unit vector. So I have it at the magnitude of 1 and the direction, and I use that to calculate where the laser has to go. Yeah, so pretty much use math everywhere, and it's always constant revision, and you can do like really cool things. So you might wanna, like, these are powers, right? The pink things, what do you collect? Hold on. Yeah, so if you wanna, like, it's very plain to just see him just lying around like this, just standing over there. So if you want to make this guy bob up and down, all you have to do is assign a sine wave with respect to this guy's y value, y position, and you can make him move like that, like this, a sine or a cos, and you're set. So we have various equations that can utilize someone's position. You can send them in random, you can set random motion and stuff. It's pretty cool. So that's it, Miss Titus. Hope you liked this. I'll see you soon. Bye.